Welcome to Parasitic Diseases. Today we're going to discuss Dracunculosis, an infection caused by Dracunculus medinensis. Dracunculus medinensis is a filarial parasite which is found throughout Africa and the Indian subcontinent. It is a disease which results in a lot of disability. It is considered a social stigma to harbor such a worm because of its pathological consequences. And as the result, it not only causes pathology of a tissue nature, it also causes psychological pathologies as well. People become ostracized from their communities as the result of being identified as someone who harbors this parasite. That means that you come from a poor neighborhood or a poor area of the world where you're unable to afford, let's say, high-quality drinking water or something of this sort. Discriminations at various levels are made throughout the world, and unfortunately that's the case in some areas where this is in the infection that is the indicator for being forced to drink something that you may not want to drink. That is contaminated water. It has a rich history of discovery. It's been known about for millennia. It's shown here as a sort of a primitive symbol for the medical world, where, as you'll recall, the caduceus is a double set of snakes wrapped around a staff. And the history of that is over here someplace. The Greeks have wonderful mythologies surrounding the discovery of medicine and how it arose. And it credits these two warrior snakes being tamed by Aeschylus. His staff says, "You may not fight anymore." As a result, the snakes are shown at peace. And that's what the doctor does. It places you at peace with regards to your disease. Or at least that's how the mythology plays out. However, the origin of the caduceus may very well date back much further than Greek mythology. And as we will see, it actually represents a cure for a particular parasitic infection, namely the one we're about to discuss. So Rudolphi, way back in the 1700s, was involved in the initial discovery of the worm itself. But it really took the efforts of Fedchenko and Leiper, the same individual who worked on Loa Loa, as we just mentioned in the previous episode, to become involved in the life cycle of this parasite, because it's not a typical filarial parasite life cycle. So unlike all of the other filarial parasites that we've discussed up to this point, where a vector was involved that had to obtain a blood meal, and the larva was deposited on the skin that then entered the bite wound, that's totally absent from this life cycle. Now we're talking about an almost entirely aquatic life cycle, which involves freshwater zooplankton, which is a fancy word for little critters that swim around that are microscopic, like copepods, for instance, and the larva of this parasite, which is produced by the female worm. And this female worm has a lot in common with Loa Loa in the sense that it stays within the subcutaneous tissues. So the adult female worm lives in the subcutaneous tissues. It locates in many infections to the lower extremities. So it's we would call that positively geotropic because it migrates towards the pull of gravity. And it locates at the lower extremities in, let's say, 80% of the cases of this infection. And there it stays. And it causes absolutely no harm whatsoever. And this worm might be quite long. It's thread-like, and it lives as a straight worm infection. It's not all coiled up like Onchocerca. It's spread out through the tissue. It's a long, serpiginous, not so serpiginous worm. So what's the big deal, right? So what happens for this worm to be able to complete its life cycle is is rather complicated. At the time of maturation for its microfilaria, because all of the filarial worms produce microfilaria, the adult of Dracunculus medinensis elicits through its secretions a blister-like lesion in the subcutaneous tissues. And this blister-like lesion then fills up not only with the fluid of the adult host that is responding to the secretions of the worms, but also with the microfilaria of the worm itself. So this is now a bathing medium for maintaining a cache of larvae, in this case microfilaria, which at a given moment can then be released to the environment. What an interesting, involved nuance for a life cycle. So what happens is that the individual that's infected notices this blister. There is some pain associated with it. And at the same time, the people who are mostly involved we're now talking about rural villages of various sorts, where water is the big issue. And water is always a big issue no matter where you live in the world, but particularly when you live in rural Africa and rural subcontinent of India, water may be miles away from where your village is actually located. So in order to get water, people every day have to migrate from their village with empty water containers and fill them at a central water facility, a well. They then travel back to their village, and that water then can last for, let's say, another week. And then another week, they have to migrate back out and get more water. So this behavior corresponds very well with the development of this parasite, because over, let's say, a period of 6 months, as this worm develops and as the blister starts to develop and as the pain from the blister starts to elicit symptoms in the host, in going from the village to the well, and in many cases it's a step well, meaning that you can actually walk down some stairs, and I'll show you some pictures in a minute, and you can soak your feet basically in the water and cool down a little bit and socialize with the person sitting next to you from the village across the way, and you can find out what's going on, and it becomes a social exchange area. If you were to submerge this blister below the surface of the water, inadvertently, perhaps, something unusual happens. The response is that it's a hypertonic solution that's created as this blister fluid. As a result, it attracts water to it, and the blister begins to swell up even more, until finally, within a very short period, let's say within a half hour or an hour, the blister will break open and release its larvae. And at that moment, the pain seems to go away. The pain of the swelling, at least, is relieved. And so it becomes associated with, if I put my feet in the water and I have one of these blisters, the blister will break, and as a result, I'm symptom-free. Now, there's some consequences of this too, which we'll get involved with regards to the treatment. What happens next is kind of interesting. Let's imagine yourself now as one of these microfilaria, and you're swimming around. Now you're not in the host anymore. You're a free-living worm. Essentially, you are a free-living worm. And your job, your charge in life, so to speak, is to infect the next host, which in this case is an intermediate host. And you do so by actually your own worm-like behavior. You wiggle and squirm and work around, and you attract attention to yourself. And these copepods are attracted to that motion. For them, that means food. So along they come, they're present, of course, in the water, and they will ingest these larvae, thinking, of course, that they're just another meal that they're ingesting. Remember why this person is sitting there at the step well, however. It's important to remember the fact that they're there to get water. So imagine all of this going on at the same time. The person comes to the step well, submerges their feet in the water, begins a conversation with their friend, and at the same time, here's this empty water vessel, and what they've done is they've submerged it in front of them so that it fills completely up with water. And if the blister had broken sometime shortly before that, then there is the possibility, of course, of including not only water in the transport back to your village, but also the entire intermediate life cycle of this parasite, because you'll scoop up all of those infected copepods at the same time. So now the parasite undergoes development inside the copepod. The infected person picks up the jug of water and somehow balances it either on their head, which places huge strain on their neck. And of course, that's a chronic problem of people living in rural villages for occupational diseases if you're a water gatherer. But what's going on inside that water vessel is very interesting. The larvae penetrate out of the gut tract of the copepod, and they develop inside the hemocoel of the copepod itself. And that might take 3 or 4 days to develop. In the meantime, of course, it might take 3 or 4 days to get back to the village, but mostly it's a day trip. But the water that's in that vessel is then drunk by everybody back at the village. And eventually the copepods will become infectious for another host as the result of the completion of the development of the larva inside the copepod. Complicated, very complicated. You'd say a life cycle like this probably doesn't exist because there's too many steps. There are too many places for it to go wrong, and yet it's such a commonly distributed parasite that you have to come to accept the fact that indeed the biology of this is rather strong and reinforcing, and the presence or absence of organisms in naturally occurring bodies of water favors the occurrence of these diverse life forms that are capable of harboring the intermediate stage of the infection. No matter where you go, it doesn't matter which species of copepod, apparently they're all susceptible. So the parasite is now back in the village, in the drinking water, and everybody's, of course, thirsty. You have to use the water for cooking. That kills the copepods, of course. And if you could boil the water prior to the time you drank it, that probably would be a good example of how to get rid of this. But because firewood is so precious, and because heating the water is a great expense in terms of energy, that's never done. The water is drunk as is and used for various purposes. Again, reinforcing the life cycle. The parasite that is released from the copepod inside the gut tract of the infected individual, it penetrates through the wall of the small intestine, and it starts to migrate throughout the body, seeking the subcutaneous tissue first, and then, as I said before, it's positively geotropic. It migrates towards the pull of gravity, in most cases, and ends up in the lower extremities, the feet, the ankles of the individual. The worm then grows up over a 4 to 6 to 8 month period. After mating, the females begin to produce their offspring that she induces a blister for. And once that person goes back to another step well and the blister breaks, it renews the life cycle. It's very, very involved, and it took a long time to figure this life cycle out. It took an even longer time to figure out what to do about it. So here's a typical step well. This one's found in India. They're all over the place, of course, but this is a spring that this step well is made around. The water wells up from the ground, essentially pure. So it's safe to drink. It's prevented from animal contamination by the fact that it's a step well that only people can get into. But of course, other diseases that people harbor that could be waterborne, namely the helminths and things of this sort, may complicate this cleanly appearance for this step well. So if the water is unprocessed, there are lots of other things that can go wrong. But the fact is that this is the environment in which the water is gathered, And this is the primary subject for a control program. Before we get to that, let's just discuss what this parasite actually does. Again, the blister is the only pathological consequence from the adult worm. The larvae do no harm whatsoever to the host because they're present in the blister itself. So it's an adult-based pathology, but as we'll see, it's not a living adult that causes the problem. And now Dr. Daniel Griffin is going to give a clinical vignette illustrating the pathogenesis of this infection.
A colleague is having management issues with regard to home care for an individual living in Queens, one of the outer boroughs of New York. This man has a wound on his foot that apparently is in need of daily care. This man reports living in Queens for about 9 months and recently developed a very painful blister on his foot. He soaked the foot in water, and this gave him great relief from the burning that he felt in the blister. But the blister did open, and the man was a little bit concerned and went to see a physician. Now, something was in the blister and now is being slowly pulled out of the wound and requires daily visits for this. A little bit of background. He is from the South Sudan, and in his home country, he had lived in a rural, impoverished area. Now, I should mention the patient himself has a good idea of what this might be, and it is something that is coming out of the wound. Now, let's talk a little bit about clinical disease with Dracunculus or guinea worm. Multiple cutaneous blisters and ulcers are the characteristic manifestations of infection with Dracunculus medinensis. Unfortunately, not really caused by the guinea worm itself, but because of the opening in the skin, you can end up with secondary bacterial infections, and these are quite common. A concern is that you can end up with the infection getting into the skin, a cellulitis spreading along the track of the worm. Now, what about diagnosis? Now, definitive diagnosis is by locating the head of the adult worm in the skin lesion in this ruptured blister, or identifying the larvae that are being released, right? So if this foot at the time of this tense blister is put into a small amount of water and out come all these larvae, you could identify those as well. Now, radiographs may also be done, and they can reveal the calcifications corresponding to the adult worms in the subcutaneous tissues, really where they have died. So this would be areas where adult worms have died. Because while the guinea worm is alive, it actually has the ability to suppress the immune system. This is going to be important when we get to the treatment. There is serology. There's a reliable ELISA test, but this isn't something that is used widely. Here's a photo and actually an ulcer. And you can see the worm in this ulcer. It's an adult worm. And this was a large, tense blister that just ruptured. A little bit more about the clinical. So you can see here in this radiograph, you can see that some of the adult worms don't actually follow and succeed in this migration. And when they die, they can become calcified. Now, sometimes there can be scarring depending upon where this occurs, and you can end up with some symptoms related to where the adults might die and where the scarring process might occur. Particularly if you think about being around a joint, for instance. Another scenario is that the adult females go through, we'll say, their proper migration. They actually get to the point where they induce this blister. And then the clinical syndrome is going to be this tense, burning blister that the person wants to put into fresh water to relieve the pain. Boom, that releases the larva. So that's the blister that we usually talk about. And then as mentioned, with this open lesion, you now have a break in the skin. And as I think you saw in the photo, it's basically a big wound. That area can become secondarily infected with bacteria. That's what can lead to death and even amputation. Now, what about treatment? The treatment's pretty straightforward. We're not talking much about drugs here. This is the time-honored winding of the worm on a thin stick until it's totally extracted. And what you're going to end up doing, and this requires a little bit, not a lot, but a little bit of understanding, is you're going to pull about 1 centimeter a day. And it is painful. When you do the wrapping around and the small pull, there's a certain amount of tension that is applied, and people have a feel for this. Not a lot of people left in the world with this expertise, but you're pulling it out just a little. It is painful. You do not want to rip open or rip apart the worm, because then you'll have the death of the remaining amount of the worm. And the worm, as Dickson has mentioned, we're talking about a meter, about 3 feet of worm. So you don't want that 3 feet of worm dead and inciting a immune response. You want to actually pull it out very slowly. And if you do the math and you say, this could take months to get out. This could take 1 to 3 months. It could take a long time for this to be extracted. So that is this concern with who you're going to get to do that every day in Queens, New York, if that's what our patient has. Now, mebendazole, just to mention, we don't want to do that. So I'm mentioning things not to do. You don't want to kill the worm. You want to extract the worm while still alive, while it's still keeping the immune system from having a vigorous response. And because of that, the wound care and pain management are important components of the care of patients with dracunculosis. And here we have a stick, and we've got a little guinea worm being wrapped around it.
So instead of working out sophisticated measures for treatment, we have worked out very sophisticated measures for controlling and preventing this infection. We couldn't do this without the intervention of beneficent people with finances, with medical backgrounds, with a desire to enable people to live better lives throughout the world. These are remarkable people that pool their resources, not only their financial, but their intellectual resources, to come up with simple, easy to institute measures for preventing the acquisition of Dracunculus to begin with. We know that you can prevent it by simply filtering the water. So if you were to collect water from one of these step wells and take it back with you to your village and then pass it through, let's say, chintz, which is a common material that people use to make their clothes with, the copepods will be trapped in the fibers of the chintz, and the water that goes through will be drinkable without the consequences for Dracunculus. Well, of course, this will not prevent the spread of dysentery and diarrheal disease-causing agents. So even though that's a tactic that works, it does not eliminate the other perhaps more serious infections of small children, let's say, for diarrheal diseases, because everybody has to drink, right? So the original program involved, from the WHO, closing off the step wells. You know, the big problem is the step well. If we could just simply close off the step wells and install pumps next to the step wells, you can get pure water. You don't have to worry about all these diseases that are transmitted by simply obtaining water from an open water source. The social consequences of closing step wells, however, would be to cut off the ability of one village to interact with another by simply meeting at these places and discussing, you know, how's it going over by you? What's new with Al? And, you know, I hope his family's okay. And, you know, et cetera, et cetera, et cetera. So they objected strenuously to the programs that were aimed at eliminating step wells and installing pumps. So by carefully inquiring what they were trying to get rid of, they eventually realized that what they were trying to get rid of would stick to these chintz fibers, and they would get rid of that. So they said, you want to get rid of Dracunculus? Fine, we will. But we don't want to give up our step wells. And so for that reason, the original WHO program, which was really aimed at getting rid of diarrheal diseases, was narrowed down to Dracunculus. And it's now a parasite which is almost absent from the world. And the filtration program has now been spearheaded by the Carter Center. And because of that, there's now a filter. It looks like a flute. And you put it down into the water and suck through it. And it prevents the copepods from actually going into your mouth and you acquiring the infection. So these devices have resulted in the rapid diminution of the incidence rate for Dracunculus throughout the world. And Donald Hopkins deserves as much credit as anybody else because he's the bona fide parasitologist that was placed in charge of this program at the Carter Center by Jimmy Carter. So thanks a lot, Donald. Thanks a lot, Jimmy. If you want to read more about this control program and how it's reduced dramatically Dracunculosis, The one thing I didn't mention in the life cycle is the fact that there could be other reservoir hosts. That's unfortunate. Dogs, in some cases, can become infected. It's not a common reservoir host, but wherever it is common, that would be a difficult thing to interface with this control program that's already in place for filtration of adult drinking water supplies. So that's addressed in this article here that you can see. We've, of course, discussed this on episode 37 in TWIP, accessible at microbe.tv/TWIP. So the next time we meet, we'll discuss nematodes of minor medical importance. Thanks for listening.